Make it so number one.
Are we recording now? Does that look good?
Yeah.
Okay. Yeah, so quiz Wednesday and exam Friday, and I switched things order around a little bit. So we're going to actually start the next chapter now. Okay? But the way in which we're going to, that's the wrong, no, I think that's right. Is it 13:14 or 14:15? I think it's 13:14. So in any case, what Dr. Einstein and I have this agreement that I give you this intro to this spectroscopy, okay? And that agreement is to kind of get you caught up in lab of the various things that we do in lab, like IR. We've already done a couple of IRs. We're going to do NMR, things like that, so you kind of know what's going on. So I'm only going to give you 2 lectures over 2 chapters. But you will not have, so this is where you want it, this is where you're like, oh, okay, I'll just go to sleep. When I say this, you won't have an exam over these 2 chapters. That's where you just go, okay, I'll just go to sleep now. I don't need to know this. So, but I will give you a good amount of homework on these 2 chapters, okay? And these 2 chapters, I do realize that you can probably just work in a group and write down the answers from somebody else, and I would never know, and you could get by and get to the final. You'll miss a few points on the final, and no one will ever know until next semester when Dr. Einstein just assumes that you know these 2 chapters. Okay? So it's real fun. It's actually some really cool stuff. My folks just got back from the Murdoch conference. Probably saw a whole lot of stuff like this. At least it was in the physical section part of the... I got a whole bunch of stuff to return to you, too, if you don't have some stuff back here. Yeah, maybe just keep them awake and return this stuff to them. I have one more quiz to grade. And so I used to teach this class, Chemistry 1200, which was for nursing students. So it was for nursing students that did not have chemistry in high school. So if they had chemistry in high school, they could jump to the 1210 class or whatever it is. But we taught this 1200 class, and it was 8 o'clock in the morning. In about 5 minutes, everyone was asleep in that class, because I would do these, get up and start doing a lecture. So I stopped doing lectures whatsoever in that class, and I gave them a quiz, gave them a homework quiz, and then broke them up into groups, and then they just kind of a fun way to teach that class and learn chemistry. But see, I didn't really have to teach them anything. I mean, I did. It was good that they knew that information, but where they were going to fail was in the next semester. So, a lot of pressure was relieved. But in this class, I actually have a lot of pressure to teach you what's in this semester of organic chemistry, because I'm somewhat certifying you that you know this stuff, when you pass this class. So when I say I'm not going to give you an exam over something, I still want you to learn it. Okay? If that's okay. All right. I'm going to go pretty fast, if I can. Let's see if I don't even know if this thing works. I'm going to go pretty fast. Oh, look at that, it works. And especially through the first part here, because a lot of it should be it's review, but it's also going to be put in a different way. Okay. So if I'm really confusing you, just raise your hand and we'll stop and go back over it. Okay. All right. So what we're talking about is spectroscopy. We're going to talk about how you look at things with various forms of light. Okay. So all of you are now looking at this through visible light. You're doing spectroscopy with your eye. That's what you're doing. If you were Geordi from the Enterprise from Star Trek, he had a visor on his eyes, and he looked in a different region of the electromagnetic spectrum. I don't know which region it was, but yeah, he could. It changed how he. So he wasn't using the visible region. He was using other regions. You go get an X-ray. Did you get it?
No.
Oh, you go do. You go get an X-ray. They're looking at you through the wavelength of light that where X-rays are. Or if you like we did our infrared spectra, that's an infrared wavelength of light. We're going to talk about nuclear magnetic resonance. Okay, so we're actually going to talk about all of these things. So we're going to talk about IR and UV. And then this one doesn't use light, but we'll talk about how that works. But we're going to talk about NMR. So nuclear magnetic resonance is the exact same thing as an MRI. So how many have had an MRI? Right? Almost pretty routine now in a sense to get an MRI. You get put into this tube. Can't wear any metal, right? Can't have any metal on you. No earrings, stuff like that. And because you're being put into a magnetic field. And then they pulse you. Do you remember, if you were in there, you heard the bong, 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 doo, 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 bong, 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 things, noises like that. They weren't actually, it was, MRIs do that for other reasons, but what wavelength of light do you think that you were getting examined with, pulsed with? Any idea? Not visible, right? Because that'd be really bright. Any idea whatsoever? It's actually radio frequencies. Okay? So you're getting pulsed with radio frequencies. So here's our electromagnetic spectrum. Up here we have our gamma rays, X-rays, so we can look deep inside tissues and things. Ultraviolet, here's your visible spectra right here, and here's this kind of cutout of your visible spectrum. And then we have infrared, microwave, and down here is where NMR is using in radio frequencies. Okay? So kind of weird that that's how it works, but that's how it works. So NMR and MRI. The reason why the name is different is because when they moved it into medical use, no one would get into a tube that was diagnosed to them that started off with the word nuclear. Right? Would you get into a big tube like that and the first word on there was nuclear?
Heck yeah.
No. Well, you would? Don't worry, this won't hurt you. Probably not. But it's nuclear because it looks at the nucleus. Not that it uses any nuclear decay or uses any radioactive materials or anything like that. It's just that it uses radio frequencies to look at the nucleus of atoms. And in you, when you do an MRI, it's hydrogen of water. And depending on where the water is, if the water's in a ligament, if the water's in other types of tissue, it can determine what type of tissue it's at, and it can get a very, through a lot of imaging, you can get a lot of very fine detail. Okay? Anyone ever had an MRI where they also then injected you with something? So the deal is they put in imaging agents into you. So they have these molecules that enhance the frequencies of various types of hydrogens that are in those tissues. So they know which ones they need to do. So if they're looking at a certain thing, deep tissue, if they're looking at a lot of vascular type things, they'll want to maybe do an imaging agent to kind of help supplement and look at it. Okay? All right. Stop me if you have questions. So this is not what our NMR looks like. We used to have one that looked just like this, but it got old and kind of finicky, and it was hard for students to use. So we have a different NMR, much smaller, but basically it has the same thing. And it has, inside, it has a magnet and these coils. And from a magnet and coils, we can do the spectroscopy. So if you went to Murdoch, this might look a little familiar because this was the keynote speaker, kind of went off this same idea, except for she was using electrons instead of nuclei. So your nuclei, this is hard to imagine maybe, but every nucleus in everything has a precession, like a spinning top, okay? And so they're spinning. It's a molecular motion that the nuclei does, okay? And they're spinning very rapidly, super fast actually, and they're spinning in all different directions, okay? So if you can imagine a top, if you spin a top on a table, it's got to spin basically up and down to keep going, and when it starts getting sideways or off axis because gravity affects it, it will then be affected by gravity and fall over or spin out or something. But because of, and it was kind of, this was mentioned actually at Murdoch, but because molecules are so, and atoms are so small, gravity doesn't really affect them. Okay? So you don't worry about, now once you get to a certain mass of those atoms together, but when you're looking at the single molecules or single atoms, gravity doesn't affect them. So all of these are just aligned randomly throughout space. But if you apply a magnetic field to it, so this is a magnetic field here, this B0 thing. So if you put this in a magnetic field, the majority of the atoms line up to the magnetic field, and then some line up opposite of the magnetic field. But they're all lined up they're not randomly in this plane anymore. They're not randomly in a vertical plane. They're all going to be horizontal or with the magnetic field, whatever field that you put that into. Okay. All right. So once you do that, you have an energy difference between the ones that are spinning up and the ones that are spinning down. Kind of a weird deal. But there's an energy difference there, and so that energy difference you can take advantage of to do spectroscopy. So if your magnet is very, very, very small, your energy difference is very, 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 very small. But as you get a larger and larger and larger magnet, exponentially, well, I guess it's linear, but it doubles more than your magnetic field doubles each time. So if you start getting a larger and larger magnet, you get a bigger and bigger difference between those energy, the up and the down energy, and so you can do better spectroscopy when the energy gap is larger. Okay, it has more resolution. You can see better. Okay, so if your energy gap is really small, you really can't see the difference between those two states. But if your energy gap is really wide, you can tell you can tell a big difference there. Okay. So we used to have the NMR that when I first got here, actually, we had an NMR that was probably down in this range that didn't work. I went out and wrote a grant, and we got an NMR that was probably out in this range. It was a really big, actually, research instrument. And we used it for a lot of years, and it was really hard for students like you to use. So when that one kind of got finicky, we came back and got one that's more down in maybe this range here. So it's a smaller magnet, but it's super easy to use, and it gives good results for what you guys are going to do in lab. Okay? All right, so each atom is going to have, okay, so I don't have a periodic table in here, so imagine a periodic table. If I have a hydrogen atom and I put it in a magnet, and I have a fluorine atom and I put it in a magnet, or a magnesium atom or a lanthanide series atom, all the same principles apply. It's just that each one of those are going to be at a different frequency. So, for example, hydrogen, what's your favorite radio station? What is it? Canyon County Country? What'd you say?
Well, it's my country station.
What is it?
99.
99.9 country music. Okay. So 99.9. Give me another one. 97.1. 102.3. So there's different information in all of those frequencies. You turn your tuner, basically, and you can get rock, country, Christian, whatever it is. That's the exact same thing for the different frequencies of the various atoms. So you turn your turn your tuner. There we go. Turn your tuner to this, and you can see carbon. You turn your tuner to this one, you can see hydrogen and fluorine, and et cetera, et cetera. Okay, so you actually can just change the instrument to look at different atoms. Okay? That should just be like some sort of epiphany for you. Huh? All right, so what else here? Okay, we're going to have to talk about isotopes of atoms as well. And we'll get there. All right. So if I put a carbon, a CH in a magnetic field, I can tune the instrument to look at hydrogen, or I can tune it to look at carbon. Okay? And if I say hydrogen, then I can see different types of hydrogens, because they'll have different frequencies as well. Okay? It's kind of like now you have TV stations. You have channel 2, and you have 2.1, 2.2, 2.3. They're all still channel 2, but they can, on a much smaller frequency, within that channel 2 band, you can get 4 or 5 different stations. So that's kind of a similar type thing. Okay? And then down here, what we're gonna have rules that will predict where and how those atoms will shift on a spectra. Okay, based on it's based on their electrons, based on the shielding of the electrons on the proton. Okay, or on the atom. So here's looking at hydrogen. Okay. So you're going to have to. There's a couple things here that you're going to have to just don't question. It's just how they started doing it. This is how they did it, and so then everybody just does it that way. Okay. But basically, and 0 is way over here on the right, and the maximum number is way over here on the left. Okay. So it goes this way, 0 and higher numbers here. And 10, 11, 12, 13, 14 doesn't really go past 14. So if you have something out at 12, that's probably about the max you're going to find it out this way. And you can have things less than 0. So they said, okay, we're going to make 0, and that's just going to be our standard right here. We're going to use TMS is going to be our 0 standard, tetramethylsilane. And then almost everything was had a higher number, higher frequency, but then they found a few things that are lower, okay, and so they have negative frequency numbers, okay. We call this a chemical shift. It has nothing to do with chemistry, actually. We're in a chemistry class. It has everything to do with frequency, but they call it a chemical shift because you're looking at various hydrogens. And then we call things that are moving this direction, moving to the left, we call that downfield. And we call things that are moving to the right, or to 0 or past 0, we call that upfield. So those are I'm going to talk about the downfield peak at 7.28. Well, it's moved downfield from, say, 0, and you would say downfield, upfield. Okay? We use chloroform pretty much exclusively as the solvent anymore. So you'll always have, almost always have this peak right here at 7.28. It's actually I don't know why it says 7.28. It's actually 7.26. But in any case, right about 7.2, there's a peak there, and we'll use, that's the standard that we use now. We don't use TMS much anymore. And I can explain it, mainly because of the advent of computers, okay? So now I have a computer, and I can say, this peak is chloroform, make that number 7.26, and then everything else gets the numbers from that. Used to be, that's the way it was. I actually did do NMRs when I was an undergraduate at Point Loma, and the way in which it worked was you put your sample in, did all that stuff the same, and then you had a pen that you actually put on a plotter, and the plotter moved, and as the plotter moved, it changed the frequency of the spectrometer, and so when it got to a frequency where there was a peak, the plotter moved. And so you always had to put TMS in, or you wouldn't know where zero was. So you got your zero peak, and then you'd hit go, and it would actually plot out your spectrum. Okay, there were no computers then. It'd been, we went to the moon and all, but that had happened already, but didn't have computers for that sort of thing. Okay. Questions? Raise your hand if you got questions. Okay, I'm going to go over this pretty fast. Let's not worry about it too much. But basically what they're saying is no matter how big your spectrometer is, we're going to get the same chemical shifts because we're going to put this through an equation. So if you have a 60 megahertz spectrometer, which is what we have, or you have a 300 megahertz spectrometer, or a 500 megahertz spectrometer, or a 1 gigahertz spectrometer, bigger magnet, you're going to get more resolution, higher resolution, but we're going to put this through this equation, and your chemical shift is always going to be the same. And if you noticed, this right here, the chemical shift is a number that is in parts per million, ppm. Has nothing to do with parts. Okay? It only has to do with you multiply this by 1,000,000 to get the number that you want. So the frequency is in a place to where, oh look, if we multiply this by 1,000,000, then we get numbers like 1, 2, 3, 4, 5 instead of numbers like 1 times 10 to the minus 6. So that's why. Okay. The person that invented, I should have looked up his name. Person that invented NMR, discovered it, and made the machine to be able to look at hydrogen, with a magnet and all. He spent his entire life getting one spectra of water, and try to do other things. And they asked him on his deathbed, said, if you had anything to do differently in life, what would you have done? And he said, I would have built a bigger magnet. Because his magnet was down here, he would have built a bigger magnet to start off with. Okay, if I can put that point towards you. All right. So here are some chemical shifts. Okay. So we said TMS. So you have methyl groups on this silane, and those we call zero. We arbitrarily called those zero. And then everything that moves, if I go higher numbers, is that upfield or downfield? If I go from 0 to 0.9, is that upfield or downfield? Downfield, right. This is down. So if I move downfield, I've got ethane moves on electronegativity, and I've got trimethyl amine. These methyls move a little bit farther down. I've got a methoxy on an ether a little farther down. I've got a fluorine a little farther down. Okay. And then if I put into the NMR propane, the hydrogens on this carbon come at 0.9. Why do the hydrogens on this carbon come at 0.9? Because they're identical, right? They're the same. They're in the same chemical environment. They are one carbon away from a CH2. This one is one carbon away from a CH2. Same CH2 in this situation. So they have to be the same. Okay? The CH2 is different. It's smashed in between these two methyl groups, and it has a little bit of a downfield shift. If I put a nitro on the end of propane, then this is a deactivating group down here. These first hydrogens really fill that nitro, and they move downfield quite a bit. The next ones fill it a little bit, and the next one fills it just a little bit as well, 0.1 difference. And so that's the effect of the shielding, deshielding of this carbon, these hydrogens. Okay, so we took electrons away, and you moved downfield. Okay. Same here. If we have chloromethane, all three of these hydrogens come at 3,1. We have dichloromethane. It moves it downfield to 5.3, and then here, if we have chloroform with 3 chlorines on here, then it moves it way down to 7.3, 7.26, 7.8 on that other graph, but you know. Okay. Or no questions there? That's perfectly clear? We're good? I scared you enough at the beginning? Okay, so here's a whole bunch more. So these are some pretty simple ones. These are all in your book somewhere. Or if they're not in your book, you can Google them. You can go to Amazon and buy tables. You can buy a whole spectroscopy book. There are standard guides for every chemical shift of every proton, carbon, phosphorus, et cetera, et cetera, et cetera. Okay? I won't have you memorize this. Oh, you guys are great memorizers. In fact, you want me to test you on memorizing this, because if I say memorize this and I have this on there's going to be 9 out of 10 of you that will just totally ace it and not know one thing of what you're doing, right? So here's the chemical shift from 0 to 13. What I want you to know, what I really want you to realize about this, and you can look up numbers, is what I want you to know is this: as you pull, if you have this electron withdrawing group, it's going to change. It's going to move those hydrogens downfield. Okay. As you add things like chlorines, it's going to move that hydrogen downfield. All right. That's really what's going on here. So, you've got a phenyl OH is way down here at 8. You've got a carboxylic acid proton is down here at 13, between 10 and 13, and aldehyde is 10 to 9, and you're going to get, these are all, once you get over here, there's a whole bunch of CH2s that are all in the same place, and it's hard to tell what they are, but as you move this one up here, you're going to go, oh yeah, a hydrogen at 5 is a vinyl hydrogen. It's a hydrogen on a double bond. Okay? So that's in your book somewhere. It's not in the one of the covers. Maybe it's in the cover. I have mine over there. We can look in a second. Okay? So that's what we're talking about. We're talking about the shielding and deshielding of protons. That's this whole thing here. This is deshielding. This is shielding of protons. Okay? Anybody see any NMRs at Murdoch in the physical science room when they popped a couple of NMRs in there? No, you guys all stayed in the biological room? Okay, you missed out. So, all right. So, for example, if you see, this is just more shielding of protons. Okay. If you see a peak around 7, it is a benzene ring. Okay? If you see some peaks around 7, and it's not chloroform, chloroform's at like 7.2, so you got to kind of be careful there. But if you see peaks there, it's a benzene. If you see peaks at 5.3, it's a hydrogen on a double bond. Okay? And the reason being is that the p orbitals sort of because their electrons are above and below these carbons, it moves electrons away from these hydrogens, and so they're a little more de-shielded. Those electrons are not shielding those hydrogens. Okay? And this is how you would tell a difference. I mean, like here, go back to this one. What happens when you get an MRI is they get all these different frequencies, and they look down and they go, oh yeah, we know if water is giving us the frequency that's here, then that's a frayed tendon. Or, so all that stuff is just the exact same. I mean, I made that up because I don't really know MRI, but that stuff it's exactly the same. You have different frequencies for the water that's in different types of tissues. So you got a shielding proton here, 9.7 for an aldehyde. Remember we said we were going to memorize all those functional groups? Here's an interesting one. So you get this molecule here, and this is the way in which you name them, which you don't know yet, but it's got 18 carbon annuline, and it's flat like this. And the way in which it works, you've got these hydrogens that are on the outside, and they are very much de-shielded out here at 9. But you've got these hydrogens on the inside that are inside this ring, and so they're very shielded, actually get a negative chemical shift. Okay, you're starting to fade on me. I can see eyes getting droopy. All right. Yes?
So the only reason, just kind of like ask a question again, the only reason it's at 0 is because that's where the arbitrary 0 point was made because of what was going on at the time. So if they used a different chemical, we might not have negative shift.
Right. Right. If they would have decided to use annuline, 18 annuline, then everything would be -3 off.
Okay.
-1, whatever that was. But they just chose, and tetramethylsilane is it's a great molecule to use as a standard because it's got 12 hydrogens, right? It's got 12 hydrogens, and all the hydrogens are exactly identical, so you get a really big peak. So a little bit, you just put like a touch of TMS in your stuff, and you get a nice, sharp, single peak. And so they just made that call back in the day. I'm sure there are other things like that now. I mean, we should no longer use miles per hour, but we do. We just decided to use miles per hour at some point. Okay. It's just the entire world, though. There is no other system. The entire world uses this system. Okay. So there's 3 things that you can get from NMR. Okay. Three things. You following me on my slides? Very good.
Right.
Very good. You can get the number of signals. Okay, so that's how many different kinds of hydrogens there are. You can get the intensity of the signal. So if you have 6 versus 3 versus 2 versus 1, okay, get the intensity. And then this part down here is going to get fairly complex. But you can tell how many neighbors a hydrogen has as well. Okay? So We'll talk about all three of these, but the first one we've already talked about. We've already really talked about how you can get different chemical shifts from different types of hydrogens. And then if you have more of one type, I mean, if you have like two that are exactly the same and three that are exactly the same, you're going to get a ratio of 3 to 2. Okay, that makes a lot of sense. This one down here is a little bit more complex. And then we're going to get into a little stereochemistry that makes it a little bit more complex. That's coming just a little bit. So here's pretty simple molecule. So we got a triple bond nitrile over here. We've got an OCH3 over here. And this is just showing you this OCH3 comes right here at 3.3, and this CH2 that's trapped here in the middle. So it's got an oxygen on this side and this nitrile on this side, so it's downfilled a little bit more. There's a little bit above 4. And then we do this thing right here, and it looks like an integral, okay, from like calculus. And it actually is just telling you, it just tells you the distance between here and here versus the distance between here and here is a ratio of 2 to 3. You can tell if you know, like for example, if you know this is a CH2, you can tell the instrument that this is a CH2, and then it will just calculate all the different ratios for you. But it's basically can't tell you exactly how many are there. It just tells you what the ratio is between them. Okay, so ratio of this side of the room and that side of the room is roughly 1 to 1. But I didn't tell you how many students were on this side of the room or how many students were on that side of the room, but the ratio is 1 to 1. That make sense? Okay. So how will we know? So we're talking about this chemical equivalency. So here we said that this propane, these hydrogens on propane were on the very end, this CH3 and this CH3 were identical. How about here? Are any of these the same? What are the same? Yeah, the CH2 here is the same, but it's different than this CH2, right? Different than that one. Or here, it's just counting the other direction here. I don't know why. Okay, and so basically the molecule, it comes back to how we name things, right? So we're going to name this differently. And so this gets a ratio, if we were to plot this out, this would have a ratio of 1 to 3. Okay, now if you know that it's a CH2, then you know it's 6 to 2. But really, when you plot it out, it's going to come out 1 to 3. It's going to come out, there's 1 CH to every 3 CH3s. Okay? All right. Questions? So this hydrogen is trans to this methyl and cis to this bromine. This one is trans to the bromine and cis to the methyl. So they're different. They're going to come at different chemical shifts. Okay? I'm going to breeze over this one. You're going to run into these when you do the homework. You're going to go, how is this possible? This shouldn't be this way. Because I'm not going to go into this in real depth because I would just daze and confuse you, I think. But turns out that these are identical, so they would be the same. Okay? But and the test in which you do that is if you change one of them into something else. If you change this blue one into, I always did the deuterium test versus a chlorine test. But if you change this one into something else, you get a chiral center. Okay? So that makes them enantiotopic. If I change this one into something else, I get a chiral center. So they call that enantiotopic. I don't have one in here. Okay. So I should have had a Dario. So if I were to change one of these and it produces a diastereomer, the two peaks then, so like for example, if I had that same molecule there, okay, and let's say that I had this was a chiral center. Let's say I have a nitrogen there, okay? So if I do the test, so I have two hydrogens here. So if I do the test, this is a different test than, well, it's the same test. So let's say I'm going to put the chlorine there. By doing that test in my brain, did I produce an enantiomer, or would I produce two diastereomers? So if I put it on one carbon, so I run my test, and I just say I'm going to replace that one with a chlorine. Then I do the test again. I'm going to replace that one with a chlorine. Do I produce, here on the board, I produce two enantiomers, right? But here on this board, do I produce enantiomers or something else? What's the relationship between this molecule and this molecule? What is it? What are they? I didn't hear it all together. Diastereomers. These are diastereomers. So if I replace this one and it ends up I get an enantiomer, they're called enantiomeric hydrogens, enantiotopic hydrogens. If I change that and I get a diastereomer, they're called diastereotopic hydrogens. And diastereotopic hydrogens have different chemical shifts. So this hydrogen and this hydrogen, even though it's both on a CH2, have slightly different chemical shifts, because the spatial relationship between this hydrogen and this nitrogen and oxygen are different than this hydrogen and this nitrogen and oxygen. So you'll run into that and you'll go, how in the world that works? And I'll just say it's diastereotopic. Okay. So here's the complex part. So if you're not paying attention to anything else, maybe you could fake it before, but you won't be able to fake this part. Okay? So pay attention to this part. Wake up and pay attention to this part. Move around. You're sleeping. Get up, jump around. Huh? I can kick you, keep you awake. You were not sleeping. I can't kick all of you. I kicked Philip Gwynn. Philip Gwynn would sit right here. Anybody know Philip? He'd sit right there, and didn't matter what I was doing on the board, about halfway through, he'd just be, I don't know, does he still do that in class? So I would kick him. It was fun. Okay, we're going to pay attention to this one. Okay? So, here I have this molecule, okay, similar to the one that we had before. There's an eraser over here. So I have what I have? No. That'd be a good molecule too, though. I have that. Just two carbons, right? Okay. So, how many different types of hydrogens do I have? These three here, is that the same as, are all those three the same? That one, and that one? You should all say yes. Those are all the same. Because why wouldn't they be? Why, if you didn't think that, why? Tell me why. Because I want to. Yes.
Because that one, like the ones I was
Um,
And so, like, on that one, the two hydrogens that would be closer, the ones that are farther to the left than the one that's like in the back.
so like, this has free rotation, which rotates all those hydrogens to be in the same environment. This is the same unless I have a chlorine there, and then I have stereochemistry. So if I have stereochemistry, they're not. So if I have stereochemistry in space, they're not the same. But I don't have any stereochemistry here. I don't have a potential stereocenter here at all. Okay, so that's the difference. If I put a chlorine here, these two hydrogens are still the same. If I put a chlorine here, those two hydrogens are still the same. That's the difference. Okay? This hydrogen is different than these three, though, right? We're going to say the hydrogen on the chlorine is different. Okay? So, N+1 rule. Okay? We're all going to do this. How many neighbors do you have? And we're going to calculate, everybody's going to calculate their splitting pattern. So we're going to go like this is one carb, this is like one thing here. So don't go back and forth. But how many neighbors do you have? One. You'd be a doublet. How many neighbors do you have? Two. You'd be a triplet. How many neighbors do you have? Okay, so we're only going to have doublets and triplets here. Okay? So, but I'm going to put you four. Let's say you four are one group right here. Okay? So you are all, the four of you are neighbors. Okay? So now, what's your multiplicity? No. No.
4.
Four. It's N+1. So you have three neighbors plus yourself. So you'd be a quartet. Be a quartet. Okay? Here, I'll split you guys up over here. Just the three of you. So you would be a what, Kat? Kit. Sorry. You'd be a triplet. You have two neighbors plus yourself. A triplet. Okay? Do I need to run this in the back, or do you get it over here?
Give him names.
We're good over here? What would you be?
So I have what, 6?
No. You're just right here. Just right here. Just on this
So
row.
I have so 3.
You just have two neighbors, so you'd be a triplet. Okay? All right. This guy goes, you go one carbon away, count how many neighbors it has. 1, 2, 3, plus itself, it's going to be a quartet. Call that a Q. That's a Q. Okay? This one, all of these are identical, but they all have one neighbor, plus, because they're identical, even though there's three of them there, I needed 3 triplets in here. I needed 3 genetically identical students to prove this point. Because these are all exactly the same, they're equivalent. They act as one, has one neighbor, so it would be a doublet. 2 peaks.
Yeah.
These are all chemically equivalent, these hydrogens right here, because this spins. So they all rotate around. Okay? So they are all act like one. They see one neighbor.
So 1 plus 1 is 2, which is double.
So the N+1 rule, that makes it a doublet.
So why are they considered one and you
Because this sees 3, it sees 3 neighbors. Even though we're identical, it sees that there are 3 different ones there. doesn't actually see it. Okay, so maybe that's where I'm kind of going off here. It doesn't actually like visually say, hey, I've got 3 neighbors. What it does do is that this, think of this as a little magnet, this a little magnet, this a little magnet. Now this is looking that direction, this is feeling that direction, and it feels 3 magnets in space. No matter how you rotate that, it's going to feel 3 magnets in space. Okay? You just asked a question. You can't be sleeping now. Yes?
What is the perspective from? Like, is it seeing its neighbor? Like, is it from the hydrogen or the carbon? Or the
The carbon's a totally different thing.
Okay.
So right now, our spectrometer is set up on hydrogen.
So it's of the hydrogen. That's where it's at. Okay.
Right. So here it is. This looks like here it is. When you blow this up, there's 4 peaks here. That's this hydrogen up here. When you blow this up, it's a doublet. It's these 2 peaks. So it's how many neighbors plus itself? How many neighbors plus itself? Yes?
If the hydrogens were different on that carbon, would it count them as neighbors?
It counts every neighbor. If it's a hydrogen, it counts it.
Well, because like I'm saying, like it's a doublet, would it count it if they like weren't all the same? Like right now they're all the same.
Yes. So that's where we're going to run into here. Remember, it's chemical equivalence. So these 2, because they're an enantiomer topic, this one, there's a CH2 here. It would look at both of those and say, so I'm going to blow you away, and then you're going to come back to class and we're going to take a quiz, and we'll talk about this in a little bit. So this CH2 here would look at this and go, I have 2 neighbors, so I have 1, 2 plus myself. It'd be a triplet. Okay? Here I have 1 hydrogen. Okay, but because that hydrogen is in space different than that hydrogen, it would see that hydrogen come, and then it would come back and say, I have another non-equivalent hydrogen because they're different in space. So this one would be a doublet of doublets, not a triplet. Just blew you away right there. Doublet of doublets, not a triplet. Okay, read up on it.